Right. I apologize for the graphics that looks modern. I think you might not like that. But so, right, I'm Lauri, and I work for NVIDIA in the Tegra graphics team in Helsinki. And I'll give a short presentation about explicit synchronization. I posted an RFC patch set to the DRI Devil and Nuvu mailing lists a couple of weeks ago. So I guess if you followed that, then there might not be that much new in this presentation. So fences are an abstract primitive that is that marks completion of an operation, a hardware operation usually, and they are used for synchronizing access to buffers. And there are at least two quite different ways how fences can be managed, and well, I suppose these terms depend on a little bit like who is talking about it, but this is what I mean by implicit and explicit synchronization. So in implicit sync, fences are attached to buffers by kernel, and kernel manages fences automatically when you submit work to the GPU or other hardware. That's the model that is currently used by the DRM model. Explicit synchronization, on the other hand, allows you to more flexibly manage and pass around fences independent of buffer objects. And the way you get fences is when you submit work to kernel, then you get a fence back, and then you can use that as a pre-fence to subsequent hardware operations. And USERSPACE can basically decide how to pass around these fences. And one example of explicit sync currently is the Android sync FDs. Right, so I will present some advantages of the explicit sync model that I think where it succeeds better than the implicit model. And also, these are the reasons that I think that the DRM should also support this explicit sync model. So basically, improved performance of bindless graphics APIs, then better alignment with USERSPACE graphics APIs, and allowing parallel processing of suballocated surfaces. And then also, I'll talk a bit about these difficulties that we in practice have when we pass buffers between engines. And I have a separate slide for each of these, so let's go them through. So traditional OpenGL works so that you bind a set of buffers to the context, then you issue a draw call, then you bind another set of textures and FBO or buffers, then you issue another draw call. And this is like old school OpenGL. And that causes quite a large driver overhead because this binding and rebinding is kind of quite slow in the driver. So bindless graphics is a set of OpenGL extensions that optimize this. So the idea is that you can bind a large working set up front and make it resident, and then you can do multiple submissions without changing the working set. And the way that this working set is referenced in the shaders is basically the shaders can even compute virtual addresses themselves to address these buffers rather than refer to some enums or API slots. So this bindless model means that usually in the driver we don't have a very good idea what exact buffers are referenced by each individual draw call. And by the way, this bindless graphics is kind of similar to the compute APIs. And these working sets can be very large, hundreds or even thousands of buffers, and they can be shared between multiple contexts and multiple channels. and all those channels should be able to process, make progress in parallel. And I'll soon give more like concrete examples of this. And so because of this working sets are so big, we don't really want to loop through all the buffers every time we submit work. So, right, so developers are demanding explicit control over the driver behavior and hardware whenever possible. So, for example, the Kronos next generation OpenGL initiative lists explicit control as its key design principle. And even current generation OpenGL is defined in terms of explicit sync. So OpenGL exposes the GL sync object, and EGL similarly has an EGL sync object that are basically just fences exposed through these APIs. And the API users are expected to express dependencies between different work submissions using these sync objects. And therefore, it's quite surprising if the kernel automatically adds other dependencies and stalls, as happens easily in the implicit sync model. And that might lead to something being fast on some other platform like Android or some other platform that uses explicit sync, and then when you run it on a DRM stack, suddenly it's like performing worse because kernel is inserting unexpected weights. Or conversely, you could have somebody who writes code for Linux on top of the DRM stack, basically relies on this implicit sync, and then when he ports it to another platform, you haven't expressed all the dependencies that you should if you use the GL or EGL APIs, and you get incorrect results. Then USERSPACE suballocation, that's a trick that we use a lot. We put dozens of small textures into one big allocation. When there are many small textures, it doesn't make sense to generate kernel level buffer objects for every one of them. However, implicit sync doesn't see the suballocation, so access to these suballocated buffers would get serialized in implicit sync, even though it should be allowed that we kind of texture from one part of the big buffer object while simultaneously in another channel writing to other parts of it. Then, especially on the SOC side, we often have many specialized graphics engines like video encoder, video decoder, 3D, 2D engines, camera perhaps. And these cross-engine use cases are, unfortunately, they're not as simple as taking a dma-buf FD and passing it to the other driver and then everything just works. In practice, you might need to flush caches, convert between linear and tiled format, convert between color spaces, or for example, in Integra, we sometimes need to decompress a buffer when we pass it from the GPU to another SOC unit that doesn't support the GPU frame buffer compression format. And I don't think these are like anything NVIDIA specific. You could easily imagine this happening when you have an SOC that has, for instance, like licensed IP blocks from different vendors. You get these kind of incompatibilities between engines. And these conversion operations are quite costly, so we really want to manage them from USERSPACE only when we know that we need to do them, rather than doing them automatically. Well, basically, my point here is that USERSPACE is already heavily involved when we have to support these passing buffers between drivers. So if we give them a little bit more control over how the synchronization is handled, then it's not adding that much. So, okay, I'll show you a practical example, simple example where explicit sync is a win. So here I have 3 channels. The time is going from top to the bottom, and all these 3 channels are using the same working set. So all of the submissions that I will put to those channels might access the same buffer, or they might not, but the working set the programmer has expressed is the same. In this example, all these channels are NuVu channels, but they could also be channels from different drivers. Like one could be a video encoder channel, and or it could be like from different processes. One could be a rendering process, and the other could be a compositor or something. So first here we submit work to the first channel. So we call NuVu push-buff kick. That's a low-level user-space DRM NuVu function. It calls into kernel, and in kernel we loop through the working set of buffers. And mind you, this might be a big set of buffers if we're having a more complex game type application, for instance. We acquire the weight wound mutex, then we loop through them again to get the fences out from the buffers, and we program weights to the command stream. Then we kick off the work to the GPU. Then we loop through the working set and store the fence. So that number 1, the blue number 1 there is kind of, when you kick off work to the GPU, you get a fence object that signals when the work will complete, and that fence you take and you store it back to the buffers before you release the weight wound mutex. Right. So the red color there kind of means the CPU overhead of locking and managing these fences and buffers. Now here we submit another piece of work to another channel, to channel 2. And the programmer has not expressed any dependencies between the 2 push buffers on the API level, but because we're sharing the same working set, we end up actually waiting for the first to complete, because in kernel we acquire the locks, then we find the fence number 1 from the buffers, and we program wait commands for that. And then the GPU host will basically stall waiting for that fence to finish until it can start processing the second buffer. And in this case, that is not what the user communicated through the API. So it's unnecessary waits. And for the third submit, the API level user has expressed this dependency to push buffer, the first push buffer, but there's no mechanism to communicate that dependency to the kernel. So instead, we just end up waiting for the all preceding work to that working set to finish. And the same thing now then in explicit sync. Here I have added a new function called NuVu push-buff kick fence that takes and emits an Android sync FD. And in implicit sync, we would attach the fence number 1 here to the buffers, to all the buffers in the working set. But instead here we return it, we package it in an FD and return it to user space. And the function also takes a dependency, the wait fence FD. So if you had a dependency, you could like explicitly tell the function that like, yeah, wait for this fence before you can process this. The second push buffer here now can run in parallel because the API user didn't pass any prefence to the kickoff function. So they can execute in parallel even though they share the same working set. And you might think like, well, do they run in parallel really on the GPU? Well, first of all, like if you have two channels, the other might be a different hardware engine. It might be an encoder or 2D engine. So in that case, at least they run in parallel. Then also, you get, even if they are, or they could be two GPUs, if the system has two GPUs, so then they also run in parallel. Also, even if you have just one GPU that has two channels, you get this low-level hardware scheduling that can alternate between the two channels. So in practice, they look like they run in parallel to the user. So the third push buffer here depends on the first push buffer. So for instance, it might be like compositing the results of the first push buffer. And this new API would allow us to express explicitly this dependency. So basically, we pass fence1 into the third submission. So that results in the third push buffer waiting for the first one to finish, but it's still processing in parallel with the second push buffer. Actually, so one thing that might happen in these kind of situations is that, so suppose the third channel here is a compositor channel, so we might have assigned a higher scheduling priority to the third channel. If they're all channels on the same GPU, then it might happen actually so that the channel 3 gets run before channel 2. So actually this bar, even though it's submitted before this one, but it might start executing and finish after the higher priority channel. So basically, if we explicitly express all the dependencies of the work, then we have more control in hardware and in kernel to organize the work so that the high priority stuff completes first. So here's a slightly different scenario. So there's just a small delta between these. So if the third submission depends on both of the previous submissions, then you can do this. Well, in the Android syncfd way, you have this sync merge function that allows you to merge two fences into one. And then that will wait both of them. This ties to what Daniel and Alex were just, I think, discussing at the end of Alex's talk. So at least on Nuvu, the dma-buf fences are not only used for synchronizing access to buffers, but also when evicting buffers from vidmem and when unmapping. So basically, when you evict or unmap, we wait for any fences attached to the buffer so that we can be sure that that it's no longer used by hardware. And only then can we evict or unmap it. So because of this, we cannot just stop attaching fences, at least on Nuvu, because it will break this. I don't know actually if this is how other DRM drivers do it, or do they have a different mechanism for synchronizing those migrations. But as Daniel and Alex were discussing, we want to optimize the common path where everything is resident and not loop through all the buffers at each submit just to notice that, well, everything is resident. So maybe we could do something like instead store a fence in a higher level object, such as channel VM, or if you want to have this kind of working set objects, you could store the fence there, and when then use some kind of dirty bits, mark a working set dirty, so that if you evict something from it, and then you need to make it resident again if it's dirty. I have to confess I'm not that experienced in this residency management because I work on Tegra and Android mainly, so we just don't do it. We just pin everything. But maybe this is something we can discuss after the talk and over dinner or something. Right, so I think these two synchronization models, explicit and implicit, are compatible. Drivers that are happy with the implicit model can keep using it, but we should allow some drivers to opt out of implicit sync. And that basically means that we need to expose some kind of kernel fence object so that can be handled separately in user space and passed around. In order to keep backwards compatibility, like if you have a DRM driver that is using explicit sync and not attaching fences to buffers at submit, then you need to be somehow able to attach those fences to buffers before you pass those buffers to a driver, an implicit driver that expects to find fences attached to the buffer. So I think, I don't remember, was it Daniel who suggested that we added a new ioctal to the dma-buf FD to attach an explicit fence to that, and similarly like extract fence from dma-buf. And then the last bullet there is basically resolve the problems of the previous slide. Like, in order to allow us to not loop through all the buffers at each submit, we need to resolve how we track residency and synchronize that. That's all I had for now. So if you want to see how Android implemented explicit sync, that's where you can find the code for the Android sync FDs. And if you want to see what we've been discussing about this on the mailing list, you can Google for that email and the thread. And I hope and I believe this is a topic that will lead to some discussions also in this conference.
Just one little question. So you were saying that you want to use the Android FD synchronization, but why do you want to use it inside the driver tube? Like, from my point of view, doing the Android synchronization file descriptor is fine for inter-device synchronization, but completely pointless for inside the same device synchronizations. Like, you can use a lot smaller, simpler, lightweight API that you expose to your driver, and you know only your driver is going to talk about this explicit API. So,
I think I had a backup slide because I knew this question was going to come up. So, yeah, from my point of view, I would be fine if we decide to have a just like gem handle for a fence, as long as we can convert that to Android sync FDs if we're running on Android.
Yes. That's definitely something you need to do. So, like, USERSPACE schedule something, use the internal driver synchronization, and then USERSPACE realize, well, I will need to synchronize with this other device, so please convert these fans to some Android file descriptors that I can pass around. This is definitely something you need.
I would be fine with that, at least.
I'm honestly not too sure that that's really a problem, because usually you don't, well, at least in GL, you kind of don't have that many outstanding things going on. So if you 10 or 100 file descriptors shouldn't hurt too badly, I thought. But maybe I'm wrong.
Yeah, I don't have any. If I had more time to prepare for this, I probably would have measured how much OpenFDs do we have just for fences on Android. I think when you boot up the Android UI, at kernel level, you have maybe in the order of 20 or 30 alive fence objects, but then you might have many OpenFDs for each of those in user space. Like, you could refer, but I don't really know how many FDs per process are you wasting just to keeping these fences open.
So from my point of view, any sane GPU for internal synchronization, all you need to give back to USERSPACE is just a single integer value versus allocating a file descriptor and doing all the initialization work that goes inside the kernel. It's pretty lightweight if you look at it, but it still requires a bunch of lock inside the kernel, a bunch of locks that can be contented actually. So between returning a simple integer and doing a file descriptor, I will definitely do a simple integer return to USERSPACE and only do the file descriptor creation when there is really a need to do inter-device synchronization.
Yeah, we had, previously on Tegra, we have this specialized synchronization hardware that we call sync points. And basically we have an ID value pair that makes up a fence. We're kind of, you can't, well, it's kind of complicated to manipulate those in USERSPACE. Like, if it's only kernel that has the code to compare two fences or check if it's expired, it's kind of, we found it easier and we found it nice in the sync FDs that we don't really have to have USERSPACE code to do that.
Oh. One problem I see with doing these lightweight interfaces, as far as I know, all the interfaces of exposing them are like on demand. So first you get an ETL sync object, and then later on USERSPACE can decide, oh, by the way, I want to Android fence for this thing. And if you just have like the numbers, then the kernel needs to keep track of quite a lot of stuff to be able to make sure that USERSPACE doesn't pull it over the table by giving it totally bogus numbers and deadlocking it somehow.
Right.
So I mean, I think on the Intel side, we'd certainly allow for like OpenGL or stuff like that. USERSPACE just keeps track of all the synchronization by emitting hardware sync points directly, and the kernel just doesn't care. But I think if the kernel should be in charge of sync, it should like create the object right away. Otherwise, there's probably going to be some fun stuff.
Right. Yeah. So that. So one of the security issues is that like, what if you allow USERSPACE to do synchronization and create fences, then you can quite easily cause deadlocks. The good thing about sync FDs or an say opaque sync fence handle thing is that USERSPACE can't just create some fence and pass it to kernel. It's very hard to create hard deadlocks if you're only allowed, if kernel only creates fences when you submit work and returns it to USERSPACE after it has actually been dispatched to hardware. That basically kind of guarantees that you can't have circular dependencies where you submit work and you say that it depends on work that hasn't yet been submitted. So yeah, we don't want USERSPACE to just create any fence and pass it to kernel.
That's it. So thank you very much.
Thanks.
So as well, late. No